Hello and good afternoon. This is room number 3. I'm afraid we haven't got a microphone, but I hope that you know where you are. The first paper is by Miguel Ángel Mañanas and Mónica Rojas. The estimated duration of this presentation is about 30 minutes. Oh, here we are. We didn't have a microphone. So I was saying this is going to last some 20 minutes, not 30, but we'll allow 5-10 minutes for questions at the end. Thank you. Very good afternoon to you all. Thank you for your attendance. Both Monica and I will try in the next few minutes to develop the reasons and the rationale of a very interesting technique, which is multi-channel electromyography and its potential use in processes of motor rehabilitation. This tool is within neuromuscular disorders, which may be due to multiple causes, such as diseases related with work life, brain damage, a cord lesion, muscle atrophy, etc. We want to know better the causes and the effects of this disease on a neuromuscular level. And this technique allows us to evaluate the technique and to follow up better the patients. This tool is a multi-channel EMG system. It is a non-invasive method. It is reliable. And this is why we believe it's interesting for clinical practice. The recordings and the analysis are relatively recent, and they were started through a European project of the 90s. This suggests that there is a wide field for investigation, for further research, and to enlarge its usage in the next few years. And this can be very helpful for future technologies. The contributions of the tool may be the following. In the control of prosthesis and orthesis, in the artificial control of upper and lower limbs, etc. Let me discuss the physiology of the motor unit. The motor unit is the smallest unit in the muscle. As you can see in the drawing, in the upper drawing, the motor unit is made up of a motor neuron of the central nervous system, which innervates a group of muscle fibers. When the CNS sends an excitation through the motor neuron, this reaches the muscle fibers, which then contract. As you may see in the lower recording, in the tracing, from top to bottom and sequentially in time, the excitation reaches muscle fibers at a certain point of the muscle, which is the innervation point, and from then on, the potential which is generated, which is the action potential for the motor unit, propagates through the muscle fibers to the tendons, to the other end, so to speak, of the muscle, as you can see in the figure. It propagates at a certain speed, between 2 to 8 meters per second. A muscle is made up of multiple motor units. These are indivisible units, as shown in the figure, which may be active or not, depending on the level of exertion required. As a matter of fact, these muscle fibers come in two types. Type 1, the slow twitch fibers. They have a low velocity of propagation. They are more resistant to exertion. And then we have the type 2, the fast twitch type fibers, which propagate the potentials at higher velocity, but they are more easily exhausted. In view of an exertion or an exercise, the CNS wants to contract a certain muscle by means of two strategies, either by means of the increase of the frequency of activation of that motor unit, as you may see in the figure. Throughout time, one sees how the different spikes in 30 seconds, the motor unit has been active during those periods. The frequency maybe between 60, 120, 150 milliseconds. But this is not the only strategy, but also the recruitment of other motor units. During sustained contraction, the number of active motor units becomes bigger or higher to make that contraction possible. In the different rehabilitation processes, we have isometric contractions where the length of the muscle does not vary. It's like exerting against an immobile ball, for instance, and dynamic contractions, isokinetic. Usually, isokinetic machines are very common in rehab systems, concentric or eccentric, or even isotonic contractions with a constant exertion. So when we record the electromyographic signal, what we record, in fact, is made up, as you may see in the drawing, is made up of a signal on the right here, a myoelectric signal, which may seem a spot or a blot or a noisy signal. And we don't know whether the muscle is active or not, or little else. But if you go to the detail, then you may observe that this signal is a sum of the contribution of different motor units, especially when this signal is recorded in the surface of the skin and when the muscle is in the depth of the tissue. And we get information from more than one motor unit. So for each block, we can have from 1 to n motor units. Each motor unit is innervated at different moments in time, and every time the motor unit is innervated, the action potential is similar. So we have trains of potentials whose sum makes up the myoelectric signal. In view of this, one of the applications we'll be looking at is to try and go back, i.e., from the basis of this recorded information, to try and detect how many motor units are active and when they have been activated in the course of time. So recording the EMG signal, as is the case with any biological system, has problems. For instance, interference from the mains, low impedance between electrodes and conductive surface, movements, electronic components in the instrumentation system. So you need to do some pre-processing of the unit. In the recording, we can use needle electrodes or surface electrodes. The needle electrodes for EMG allow us to get this typical signal. On the surface, in a non-invasive fashion, and this is what we use in our center, we get this type of recording. The origin of the information is the same. However, the recorded signal is different. Possibly, this will give us different information. So we have a duality, intramuscular EMG or surface EMG. The intramuscular EMG is more well known in the clinical practice. In medical centers, this is usually used for EMG disorders. When you prick with a needle, you get closer to the muscle, and therefore the information will be clearer for that motor unit, but you will lose overall information of the muscle behavior. The crosstalk level will be lower. Crosstalk means adjacent muscles providing signal, which are of no interest. The crosstalk is kept at a minimum with intramuscular devices. However, surface EMG provides interesting information. First, it is a non-invasive technique, therefore painless, but it is only limited to surface muscles. It allows us to look at the activity of motor units in a wider area. We can reckon the conduction velocity of different potentials when they are associated to myoelectric fatigue. We have a high level of crosstalk generated in neighboring muscles, which we can try to reduce. We also have information, anatomical information about the muscle, the innervation areas, the length of the muscle, its composition, its fiber architecture, tendons, etc. And we can break down the whole recording if you have a good number of recording channels. So you need to have the surface EMG, but in a multi-channel fashion, as you will see in a minute. Which are the factors which have an influence on surface EMG? The conductive volume, the control of motor units like recruitment, the use of the different frequency of application, etc. The EMG signal, the bandwidth, is up to 2 kilohertz. Propagation causes a filtering effect. We can record millivolts for the EMG signal, and the signal requires stationary or non-stationary techniques for its analysis. This is a drawing showing how the excitation propagates through the nerve fiber, reaches the innervation zone, this yellow point, or green rather. We see this matrix of leads or electrodes. You record the potential, which appears right now, very close to the innervation area, and as it propagates to both ends of the muscle, you may see that as time goes by, the same potential is being recorded in the different channels of the electrode or lead matrix. This would be a real case. We can detect the velocity of conduction in different circumstances. Here we have 2 innervation areas. We see the propagation of the signals. The lead matrices being used are linear matrices. These are silver-coated. They permit contact with skin. They can easily be moved about. These are other linear matrices which, by means of adhesive foam, hold better onto the skin or point of interest. When we need to make the recording whilst the muscle is being moved, so the signal is very good. These are the matrices which are smaller, depending on the length of the muscles. And we have matrices in 2 dimensions, which allow us not only to try and align the matrix on the muscle, but also to obtain information from a space where there may be more than one muscle. Which are the variables of interest? We want to know to quantify that information.